Hello, my student. I will start now to explain for you the chapter 8 DC motors and generators part 2. We will continue the topics of chapter 8. We will start with section 814, the series DC generator. Okay, already we have covered the two types, shunt DC generator and separately DC generator. Now we'll continue the remaining types of the DC generator, which is the series generators. Okay, so a series DC generator is a generator whose field winding is connected in series with the armature. Since the armature has a much higher current than the shunt field, the series field in a generator of this sort will have only a very few turns of wire, and the wire used will be much thicker than the wire in shunt field. Since the full load current follows through it, a series field is designed to have the lowest possible resistance. The equivalent circuit of a series DC generator is shown in figure 9. Okay, we will just maximize or zoom in to see the equivalent circuit of a series DC generator. As you can see here, we have, this is the RA, armature resistance. It will be in series with RS. Okay, this is the series, okay, resistors. It will be all in series. As you can see here, we will have here IL will equal IA will equal IS. Okay, load equal armature current equal the current of the series okay, resistors here, or okay, so all are equal here because they are connected in series. Also, we have for the terminal voltage, we have VT equal EA minus IA multiply the sum. Now we will add them together because they are connected in series. RA plus what? RS. This is the R total. Also, we have here, as you can see, IL equal what? VT over what? VT over R load. This is what here? Ohm's law. Okay. As you can see also, this is the two equations here. It is written here also, where this is the the summation of the R total. Okay, will be now RA plus what? Plus RS. Okay, let's now move to the next slide. Now let's talk about the terminal characteristics of a series generator at no load and as a load increase and full load. Okay. Okay. There is no field current, so terminal VT is reduced to a small level given by the residual flux in the machine. VT will equal, at this case, VT will equal what? EA, where EA equal what? This is by K flux residual omega. We have what? A small here voltage, okay, because of what? Residual flux. As you can see here from the figure, this is the very important, this figure here. As you can see, we have, this is the EA at 0 here, EAO, Okay, we have a little voltage here, VT, because what, guys? Because of the residual magnetism here, because the flux here. As you know, if we have a flux, then we will have what? Then we will have EA, okay, armature what? Voltage, okay? Okay, as the load now, as the load what here, as the load what here increase, okay, the field current rises, okay, so EA rises rapidly. The drop voltage, okay, IA multiply RA plus RS, or in other words, IA multiply the R total here, goes up too, okay? So the drop voltage will increase also, okay? But at first, the increase in EA goes up more rapidly than the rise of the voltage drop, IA, R total. So VT also increases. After a while, okay, after a while, the machine approach saturation, okay? It will reach what? Saturation. Where is the saturation point here? This point, guys, at this, okay? This is the saturation point here. And EA becomes almost constant, okay? At that point, the resistance drop is the, okay, the predominant effect, and VT starts to fall, okay? VT starts to fall, okay? After saturation here, as you can see, VT will start to fall. This type of characteristic is shown in figure, this is the figure 10. It is obvious that this machine would make a bad constant voltage source. In fact, its voltage regulation is a large negative number. This is the disadvantage of the series DC generator. It has what? A large negative number. Okay. Oh, okay. By the way, this is the terminal characteristics of a series DC generator. This is very important. Figure 10. Okay. Let's move to the next slide. Okay. So series generators are used only in a few specialized applications where the steep voltage characteristics of the device can be exploited. One such application is what? Arc welding. This is the application of what? Of the series what? DC generator, arc welding. Okay. By the way, this is another figure here. You can see a series generator terminal characteristics with a large armature reaction effects suitable for electric welders. Okay, this is with here, as you can see, with armature reaction, and this is with what? With the IARA drop. Okay, as you can see, the armature reaction will affect what? The VT, or terminal voltage. Okay, this is another figure. Okay, now let's move to the next section, which is what here, guys? 8.15. This is the cumulatively compound DC generator. Okay, this is the last type of the DC generator, which is compound DC generator. It has two types, cumulatively and differentially. Okay, we'll discuss each one now. This type is a DC generator with both series and shunt fields connected so that the magnetic fields from the two coils are what? Additive. Okay, we'll see now figure 11 shows the equivalent circuit of the cumulatively compound DC generator in the short shunt. We have short shunt connection and we have long shunt. The dots that appear on the two coils are related with the direction of the magnetic fields of that coil. Current flowing into a dot produces what? Okay, produces a positive magnetic field. Notice that the armature current follows into the dotted end of the series field coil, and the shunt current IF follows into the dotted end of the shunt field coil. The other voltage and current relationships for these generators are illustrated in figure also 11. However, there is another type of connection where the series coil is inside the armature circuit and feeding the shunt coil, and it is called what here? This is long shunt connection. We have so here two types here, short shunt and long what here shunt. Let's go to the figures here. We have two figures here. So okay, let's make zoom in here. Okay, so figure 11, this is what, guys? This is the equivalent circuit of a cumulatively compound DC generator in a short shunt connection. Okay, this is short shunt, as you can see here. Okay, if the series, this is series, yes, series connected after what here, the shunt. Okay, it will be what? Short shunt. Okay, we have IF VT over RF. IA will equal here, guys, IL plus IF. This is what, shabab, this is what here, Kirchhoff's current law. Okay, as you can see here, IA will go this point here, will divide to what here, IL, and what here, IF here. This is IF here, will goes here. Okay, this is IF. Okay. Also we have, guys, here VT equal EA minus what? EA minus IA, RA plus RS. IL will equal here IS. IL here also for equal what? VT over what? RL, Ohm's law. Okay, let's see the next types here. It will okay it will have the same equations. Okay, for long shunt, as you can see here, this is the what? Series. Okay, if it is if the shunt here, this is the shunt connected after the series, it will be what? Long shunt. This is another type. This is a long shunt what? Connection. I equal IL plus IF. VT will be the same. IA will equal now here. IA will equal IS. At this type, IA will equal what? Will equal IS. For short shunt, what? IL will equal what, shabab? IS. Okay, guys. Also here, IF equal VT over RF, IL equal what? VT over RL. Okay. So keep your mind these equations. Now, next slide. Okay. A cumulatively compound DC generator is a DC generator with both series and shunt fields connected so that magnetomotive forces from the two fields are additive. Okay, therefore the total magnetomotive force on this machine is given by, this is the force here, then it will be what here, this field plus what? Series minus what here, minus what? The armature reaction. Okay, the magnetic force of the armature reaction. Okay, here minus. Okay, where this is, okay, this is the shunt field magnetomotive force, and this is what? Series field magnetomotive force, and this is what here? Armature reaction magnetomotive force. The equivalent effect, okay, shunt field current for this machine is given by, okay, equivalent what? Field current will be IF plus N series over NF multiply IA minus what? Armature force over magnetic force armature over NF. Okay, the other voltage and current relationship for this generator are what here? This is again repeated here. I equal IF plus IL. VT will equal EA minus IA multiply RA plus RS. IF will equal VT over what? Over RF. Now let's talk about the terminal characteristics of the cumulatively compound generator. Okay, we'll consider the short shunt connection. So when the generator runs at no load, the current in series coil is what is 0. The shunt coils, however, carrying exciting current IF, which produce the field flux, just as in a standard self-excited shunt generator. Okay, as generator is loaded, the terminal voltage tends to drop, but load current IL now follows through the series field coils. If the series magnetic field is in the same direction as that of the shunt magnetic field, then we call this generator is what here? Cumulative. Consequently, the field flux under load rises above its original no load value, which rises the value of what? Of EA. If the rises coils are properly designed, the terminal VT remains practically constant from no load to full load. The rise in induced voltage compensates for armature IR drop. In some cases, we have to compensate not only for the armature voltage drop, but also for what? IR drop in the feeder line between the generator and the load. The generator manufacturer then adds 1 or 2 extra turns on the series winding so that the terminal voltage increases as the load current rises. Such machines are called what? Over compound generators. If the compounding is too strong, a low resistance can be placed in parallel with the series field and has the same effects as reducing the number of turns. Okay, for example, if the value of the derivative resistance is equal to that of the series field, the current in the latter is reduced by half. Okay, we have figure 13. This is the load characteristics of some shunt and compound generators are shown in the figure what? In figure what? 13. Okay, let's move to the figure here. We can see the figure 13, terminal characteristics of the cumulatively compound what? The compound DC generators. This is VT, and we have IL. This is the shunt, and this is what here under compounded, and this is for flat compounded. Okay, now let's move to the voltage control of the cumulatively compound DC generator. How we can control the voltage here? Okay, so the techniques available for controlling the terminal voltage of cumulatively compound DC generators are exactly the same as the techniques what here, guys? As the techniques for controlling the voltage of shunt DC generators. This is the same techniques here. Number 1 is change the speed of rotation, and 2 is change the field current. Okay, as discussed for what here? For a shunt DC generator. The speed of rotation, and this is clear here from the equation here, E equal K flux omega. Okay, so as we increase the here omega, the rotation, it causes the terminals VT will increase also. Okay, for the field current, a decrease in RF, so IF will goes down. Okay, IF here to increase. Sorry, here a decrease in RF, cause IF to increase, which increase the total magnetomotive force in generator. Okay, so next slides here. So in section, we'll start with a new section, which is here 8.16. This is the last type, the differentially compounded DC generator. A differentially compound DC generator is a generator with both shunt and series field, but this time their magnetic-motive forces subtracted from each other. Okay, now subtracted from each other. Equivalent circuit of a differentially compound DC generator is shown in figure. Here we have the figure. Also, we'll see this figure, inshallah. Notice that the armature current is now following out of a dotted coil end, while the shunt field current is following into a dotted coil end. Okay, we have the equations here. If the force net will be here now will be what? Minus. Okay, for cumulatively will be positive, and for differential will be what? Minus here. Force minus the series force minus what here? The magnetic force of armature reaction. Okay, the equivalent shunt field current due to the series field and armature reaction is given by what here? I equivalent will equal minus N series over NF multiply IA minus what? Magnetic force, okay, of armature over NF. Also here the effective shunt field current, okay, will be now here for minus, okay, IF minus NC over NF. Okay, terminal characteristics of the differentially compound DC generator. Okay, so as IA increases, the drop increases as well. This increase tends to cause the terminal voltage VT, what here shabab, to decrease. VT will decrease. As IA increases, the series field magnetic motive force, okay, will increase. 2. This increase in series field magnetic motive force reduces the net magnetic motive force on the generator, which in turn reduces the net flux in the generators. A decrease in the flux decreases what? EA, which turns decreases what here? VT. So since both these effects tend to decrease VT, the voltage drop, okay, as the load is increased on the generator. So a typical terminal characteristics for a differentially compounded DC generator is shown in figure here. The following figure here, as you can see, guys, zoom in for the figure here. This is the figure. As you can see, for differentially, we start with VT. Okay, we have some value, okay, for VT, but it will go rapidly towards low value for VT. Okay, this is for shunt. Okay. So now the voltage control of differentially compound DC generator. Okay, how we can control the differential compound DC generator. Even though the voltage drop characteristics of a differentially compound DC generator are quite bad. Okay, as you can see, guys, from the figure, it is quite bad. It is still possible to adjust the terminal voltage at any given load setting. The techniques available for adjusting terminal voltage are exactly the same as both as what those for what shunt and cumulatively compound DC generator. This is the same. Okay, guys, change the speed of rotation omega, change what? The field current IF. The same techniques used for what? For cumulatively and shunt. Okay, guys, now we will move to solve some okay, we have problems here, some problems, problem 1 and problem 2. Okay, and I will give you guys as an assignment, you have to solve and submit it through the Blackboard. Okay, so let's read the question. Problem 1. A long shunt compound generator delivers a load current of 50 ampere at what? 500 volt, and has armature series field and shunt field resistance of 0.05, 0.03, and what? 250 ohm. Calculate the generated voltage and armature current. Generated what? Voltage and armature what, okay, armature what current, IA, okay. As you can see, this is the figures of what, guys, of the long shunt. Okay, long shunt is mean what, the shunt will be what, after what, after the series. Okay, so it is giving from the question, we have VT terminal 500 volt, I load 50 ampere, RA 0.05. Okay, as you know that the RA will be it will has what, a low value. RS 0.03, R shunt what, 250 ohm. So first we have to find what, guys, I shunt. Okay, I shunt. I shunt, it will be equal what, VT over R shunt. Okay, VT over what, R shunt. We have VT, okay, we have VT equal what, 500 over 200, okay, 250. The answer will be what, guys, here will be what, 2 ampere. Okay, 2 ampere. So now RA here, RA will equal what, I shunt what, I shunt plus what, I load. This is I shunt, by the way, guys, here I shunt. Okay, this is what, I shunt, and this is what here, guys, this is I load. Okay, because it is here VT parallel, so I will use the same, we have used the same what, voltage here. Okay, so IA will equal now I shunt, okay, I shunt plus what, I load. Okay, Kirchhoff's current law. So 2 ampere plus what, 50 ampere. Okay, because it's given here from the question 50 ampere, so 52 ampere will be IA. Now we will write the equations to find what, the what here, generated voltage EA. We know that VT equal EA minus IA multiply RA plus RS. So just move this to the other side. It will be what, plus here. We have this equation now. EA equal what, VT plus IA multiply RA plus RS. So 500 VT plus IA we already calculated, IA 52 multiply the summation of 0.05 plus 0.03. Okay, so this is the final answer. Generated what, generated voltage EA equal what, 504 or 504.16 volt. Okay, 504.16 volt. This is another problem here. This is for problem 1 for long shunt. This is for what here, guys, for short shunt. Okay, again here we have given what here, 30 ampere. This is what, guys, 30 ampere. This is I load, and what, 220 volt. This is VT, and also we have RA, which is 0.05, RS 0.3, R shunt 200. Okay, R shunt. This is here, guys. This is the shunt here. This is the shunt here, which is equal here to 200 ohm. Okay, you have to find what, shunt, IF or I shunt. Okay, guys. Okay, IF or I shunt equal what, VT over R shunt. 220 VT, because VT is parallel, guys, parallel, so we will use the same value of the voltage. VT over R shunt equal 1.1 ampere. This is the answer. Then IA R shunt equal what here, R shunt, I shunt plus I load, 1.1 plus 30, it will be 31.1 ampere. Okay, this is IA. EMF, okay, it is the same meaning, guys, induced voltage, EMF. Okay, this is electromotive force. Okay, EMF. Now VT equal EA minus IA RA minus what now here, IL RS. Okay, we have now different equations for what, for a short shunt. I need to find EA, so EA will be what, VT plus IA multiply RA plus what, IL multiply RS, because IA now not equal what, guys, here, IA are not equal IL, like what here, like what the long shunt. So EA will be 220 volt plus multiplication of IA RA and what ILRS. So the answer will be what EA equal 230.56 volt. Okay guys, so this is the end for explanation of part 2 of chapter 8. Okay guys, I will upload an assignment for you, a problem, and you have to solve and upload this your solution through the Blackboard. Thank you and see you again.